Hello and welcome to a Koios tuition video on circle theorems. In this video we will go through 6 circle theorems, solving 2 questions related to each theorem. To solve these questions we need to remember some general geometry. We'll need to involve knowledge on angles and shape, such as inside angles in a triangle add up to 180 degrees, and that inside angles in a quadrilateral add up to 360. If you feel like circle theorems are a bit too difficult and confusing, it might be that you need to revise geometry and angles a bit more beforehand. With all that being said, let's crack on with some circles. There isn't a better way to learn these theorems than to actually do the questions. So, starting with the first question, the angle ABC is equal to 30 degrees, find angle AOC. We know from the theorem that the angle at the center, this one here, AOC, is twice as big as the angle at the circumference, ABC. So the angle AOC is equivalent to 2 angles ABC. And we know that the angle ABC is equal to 30 degrees. So AOC is 2 of 30 degrees. AOC is equal to 60 degrees. And that's the answer. Question 2 of that theorem. The angle FOH is 110. Find the angle FGH. Again, from the theorem we know that the angle at the center, FOH, is twice as big as angle FGH. We know that FOH is 110, so 110 degrees is equal to 2 of FGH. Now to get FGH on its own, we divide both sides of the equation by 2. And 110 divided by 2 is 55 degrees. 2 loads of FGH divided by 2 is FGH. So, the angle FGH is equal to 55 degrees. So, Theorem 2. We have a question that tells us that the line AOC here is the diameter of the circle that passes through the center, and we're told to find angle ABC. This bit here, the line AOC, the diameter, plus this half of the circle make a semicircle, which tells us that the angle here is a right angle. That's all there is. Angle ABC is equal to 90 degrees. Of course, you'd have to give a reason, and that is an angle in a semicircle is a right angle here. But there isn't any more working out to do. And another question, the line FG here is the diameter of the circle. Find the angle FHG. Again, if FG is the diameter and it passes through the center of a circle, that makes this angle here a right angle. Any angle that's drawn from FG is a right angle, so FHG is equal to 90 degrees. And that's it. So any angle we draw from these two lines, FG, would be a right angle. This one, this one, this one. They're all 90 degrees. And that's all there is to this theorem. And on to Theorem 3, the first question. The angle ABD is equal to 27 degrees. Find the angle ACD. Now, both of the angles ABD and ACD are drawn from the same arc of the circle here, right? They both start and end at the same point, and so the theorem tells us that these angles are equal. ABD is equal to ACD. Now we're told that ABD is 27 degrees, so that must be the value of ACD. and that's it. And the reason would be angles from the same segment, from the same arc, are equal. And another similar question. The angles ZXW and ZYW are up to 70 degrees. Find the angle ZYW. Now, once again, the angles ZXW, this one, and ZYW, this one, they are drawn from the same arc of the circle here. They both start at Z and then at W, which makes them equal. ZXW is equal to ZYW. And we're told that they add up to 70, so ZXW plus ZYW is equal to 70 degrees. We can substitute ZXW for ZYW here, so we end up with ZYW plus ZYW is equal to 70 degrees. Add them together, we get two loads of ZYW equals 70 degrees. Divide both sides of the equation by 2, and we end up with the angle ZYW being equal to 35 degrees. And that's it. And on to Theorem 4. Opposite sides in a cyclic quadrilateral add up to 180. They're complementary. So the question tells us the angle ABC is 75. This angle here is 75, and we need to find ADC, this angle here. Now, as it happens, these two angles are opposite, which means they add up to 180. ABC plus ADC equals 180 degrees. And we told the value of ABC, so we know that 75 degrees plus ADC is equal to 180 degrees. Doing this step by step, we would subtract 75 degrees from both sides of the equation. And we end up with ADC being equal to 105 degrees. And then, if the question asks for a reason, you'd write opposite sides, opposite angles of a cyclic quadrilateral add up to 180. Okay, question 2 of this theorem. The angle FIG, this one, is 72.5. The line GI is the diameter of the circle. Find angle FHG, this one here. Now, before I start, I forgot to mention in the previous question, in case you didn't know, a cyclic quadrilateral is one whose vertices all lie on the circumference of the circle, which in this case is F, I, H, and G. All of the four vertices lie on the circumference, which makes this a cyclic quadrilateral. So, going back to the question, the angle FIG is 72.5. Find the angle FHG. What about this middle sentence here? Line GI is the diameter of the circle. Now, you might think, oh, this is a semicircle. One of these angles must be 90 degrees. That only applies to triangles. That theorem, Theorem 2, only applies to triangles. This is a quadrilateral. This sentence here is just to confuse you. You can ignore it for this question. So, as it turns out, we know this angle, we're looking for this angle, and they are opposite in this quadrilateral. They're on the other sides of the quadrilateral, which means they add up to 180. FIG plus FHG add up to 180 degrees. FIG is 72.5 plus FHG is 180. Subtract 72.5 from both sides of the equation, 72.5 degrees, and we end up with FHG being equal to 107.5 degrees. Again, the reason for that is opposite angles in a cyclic quadrilateral are complementary. They add up to 180. And on to the next theorem. Question says, line DAE here is a tangent to the circle at point A. The angle DAC, this one here, is equal to 55. Find the angle ABC. Here, there isn't that much working out to do in this question, because from alternate segment theorem, you know that the angle DAC is equal to the angle ABC. These two angles here must be equal. So DAC is equal to ABC. ABC is equal to the angle DAC, 55 degrees. And your reason is alternate segment theorem. You'd write it. And that's it. And on to the next question. Again, this is alternate segment theorem. The line P and Q is a tangent to the circle at N. The lines MN and LN are of the same length. They are of the same length. The angle MNL here is 30 degrees. Find the angle QNM. So, we know what this angle is. We have to find this angle here. So, to solve this question, what we have to realize is that the triangle MNL here is an isosceles triangle, because these two sides are of the same length. If this is an isosceles triangle, these two angles here are equal, and because it's a triangle, the three angles add up to 180. So the angle LMN plus the angle MLN plus the angle MNL add up to 180 degrees. Now, we know that LMN and MLN are of equal length, so instead of writing LMN, MNL, I'm going to write 2LMN, right? Add on to that the angle MNL, which we know is 30 degrees. That adds up to 180 degrees. Now to solve this, we subtract 30 degrees. Oops, that's not a 30. 30 degrees from both sides of the equation. We end up with two of angles LMN are equal to 150 degrees. Divide both sides of the equation by 2, and we know that LMN is equal to 75 degrees. That's not the end though, because we need to find the angle QNM. From alternate segment theorem, we know that QNM is equivalent to MLN. This angle is equivalent to this angle, and this angle here would be equivalent to this one here. Now, QNM is equal to the angle MLN, but because it's an isosceles triangle, MLN is equivalent to LMN, which is 75 degrees. And your reasoning for this would be, for this equation, the reason is angles in a triangle add up to 180, And the reason for this one would be alternate segment theorem. And that's it. Okay, first question of the last two theorems. The line BA is a tangent to the circle at A. The line BC is a tangent to the circle at C. The angle ABC, this one here, is equal to 40 degrees. Find the angle ADC, this one here. The first thing we need to do is draw lines from A to the center of the circle and from C to the center of the circle. And we've produced two radiuses, two radii, OC and OA. From the theorem, we know that the angle between between the radius and a tangent that meets the radius, OA and BA, is 90 degrees. Likewise, the angle between OC and BC is 90 degrees. And now we have a shape that I'm going to highlight in blue. BAOC. Yeah. This kite shape, this four-sided shape, a quadrilateral, all of the angles inside this quadrilateral add up to 360. So, the angle ABC plus the angle BCO plus the angle COA plus OAB add up to 360 degrees. All of the angles inside a quadrilateral add up to 360. Angle ABC is given to us, it's 40. Angle BCO, we know that it's 90 because of the theorem. 90 degrees. Angle COA is unknown. Angle OAB is 90 degrees. And together they should add up to 360 degrees. 40 plus 90 plus 90 gives us 220. That's 360 degrees. And if we subtract 220 degrees from both sides of the equation, COA is equal to 140 degrees. But that's not the end of the question. We need to find the angle ADC. And what we now see is that the angle AOC and ADC are related through the first theorem. That is, the angle at the center of the the angle at the center of the circle, AOC, is twice the angle at the circumference, ADC, drawn from the same arc, the arc being AC. So, angle AOC is equal to 2 of ADC. We know that AOC or COA, the same angle, is equal to 140. That's equal to 2 of ADC. Divide both sides of the equation by 2, and we end up with ADC being equal to 70 degrees. And if you had to give reasons, this reason is angles in a quadrilateral add up to 360, and this reason would be angle at the center is twice the angle at the circumference from the same arc. There you go. Okay, on to the last question. The lines ZP and ZQ are tangents to the circle at P and Q. The angle PNQ is 100 degrees. This angle here is 100 degrees. Find the angle PZQ. PZQ. This angle. Right. Again, the first thing that we want to do is draw lines to the tangents from the center of the circle, OP and OQ. And we know that the angle OPZ and OQZ will be right angles. Why do we need to know that? Well, what we see is that the shape P and QM, well, that was a really bad straight line. PNQM. This is a cyclic quadrilateral, so opposite angles add up to 180. So, from this we know that the angle PNQ plus the angle PMQ add up to 180 degrees, and we know that PNQ is 100 degrees. 100 degrees plus PMQ equals 180 degrees. Subtract 100 from both sides, and we know that PMQ is equal to 80 degrees. Why is that important? Why is this angle important? Because now is second. So let me just highlight it. This was the first reasoning, and the reason for that is opposite angles in a cyclic quadrilateral add up to 180. The second reasoning is that the angles PMQ and the angles POQ are drawn from the same arc of the circle, which means that angle POQ is twice as big as the angle PMQ. And we know that PMQ is 80 degrees, POQ then must be twice that. POQ is equal to 160 degrees. So this is our second reasoning, and the reasoning for that was the angle at the center is twice the angle at the circumference drawn from the same arc. And the last thing we're going to do is, well, let's just highlight the angle POQ, this one here. The third thing we're going to do is consider this blue quadrilateral here, POQZ. It's a quadrilateral, so the angles add up to 360, and the angles are POQ plus the angle OQZ plus the angle OPZ plus the angle PZQ. And the sum of the inside angles of a quadrilateral add up to 360 degrees. POQ is 160, OQZ is 90, OPZ OQZ are 90 because the angle between the tangent and the radius that meets it is 90. OPZ is 90 because the angle between the radius and the tangent is 90 degrees. And PZQ is unknown. It's the angle we need to find. They add up to 360 degrees. The sum of 160 plus 90 is 340 degrees. So 340 plus PZQ is equal to 360 degrees. Subtract 340 degrees, and we can tell that PZQ is equal to 20 degrees. There you go. And this was our third reasoning, and the reason for this is that angles in the quadrilateral add up to 360. And that's the end of the question.